Hello, welcome. This is SND College of Engineering and Research Center, Yeola. Lecture series for first year engineering from Physics Department, Engineering Physics. I, Dr. Chaudhary Vivek Sitaram from first year Engineering Department. So today's topic is about finite square well potential, that is square well potential. For a V finite, as we know, in a potential well, when we have seen the Heisenberg uncertainty principle. So in Heisenberg uncertainty principle, we cannot measure the two parameters simultaneously. And here we consider the potential, that is, it is a finite, V is equal to finite outside the well, means that it is having the infinite potential. So finite square well potential. The solution to this is inside the well the same, have different outside. The boundary conditions for the wave function and its derivative continuous. As we know, for any derivative, it is having the wave function psi, its derivative should be continuous for the given range of that well. So now it gives the quantization for E is less than V. So no longer the wavelength, where lambda is the wavelength and lower energy, finite number of energy levels. Now, as we know from the Schrodinger's equation, that is minus h cross square upon twice m d2 psi by dx square is equal to E minus V of psi. So if E is energy is greater than potential well V, then the solution is equal to sine of k0x cos of k0, and its solution is, if we put over here, then E0 as h cross square k0 bracket square upon twice m is equal to E minus V by rearranging this. So here we get the k0, which is equal to as a under root the twice m into the bracket E minus V upon h cross. So, and for the energy less than the potential well, here we get the solution K2, which is equal to twice m into V minus E and divided by H cross. Now, if we consider the boundary conditions, want the wave function and its derivative to be continuous, often a symmetry such that solutions at plus A also given 1 at minus A. Often can do the ratio, and that can simplify the algebra. So psi minus is the boundary to say psi plus is the boundary. So delta psi by delta x is equal to delta psi of plus value upon delta x. So 1 upon psi minus delta psi minus up to the boundary conditions upon delta x is equal to 1 upon psi plus delta psi plus boundary conditions of dx. Now, the finite square well potential. So here inside there is a particle. So particle is inside the square well. So it is present over there. So the wave function is present over there. So its solution is A sin kx and B sin cos x. So if we apply the boundary conditions to this, for x is less than a by 2 and x is greater than a by 2. So x is greater than a by 2 and x is less than a by 2. So we get the values of wave function, that is solution for above wave function. Psi of x is equal to c e raised to k2x plus b e raised to minus k2y. And if we apply the wave function psi tends to 0 as x tends to plus minus infinity. So the value of d and f automatically tends to 0. And at the last we get its derivative by putting its derivative in the final equation, the finite square well potential, the psi x is equal to a sin kx in the well. So the wave function, the particle is present in the well, so it is having the wave function psi x whose behavior is like the a sin kx. Now we have to find the value of the coefficient a and the value of k. But here we directly go for the k cot kx. So quantization, and second from the wave function psi is equal to b cos kx in the well. So here directly we can come to know that it is having k1 and k2 both dependent on the energy E. Quantization sets allowed energy levels. So in between E and V0, so energy E is equal to h cross square pi square n square upon twice m square. It should be less than or equal to potential well V0. So finite square well. So energy E is equal to h cross square pi square n square upon twice m square. It should be less than V0. And so for n number we get the n square, and from this finally n is equal to 1. Only one bound state is there. So if we observe over here in the figure, so the particle is having this red one, it is only one bound state. It is only one bound state. Okay. So now if we consider an electron having the velocity energy 100 electron volt, that is, and width of 0.2 nanometer. So delta is, that is the, we can get over here 1 upon b is equal to h cross upon under root twice m v minus e. Then its value, it is having only one state. So now if we consider this, so delta function of the potential, there we will get the only one spike. So delta function for the potential too, so it is having different. So now there is a barrier of the well. So this barrier we have to see, and this barrier energy less than V, energy greater than the, but in this barrier the wave function is present over here. So this barrier we can get the psi as a wave function, and k0 is the constant, where it is equal to under root twice m e minus v upon h cross square. We will have reflection and transmission at x is equal to 0, but at d the term unphysical, and so d is equal to 0. So for x is equal to 0, due to the high potential well, here the potential well is high, so that's why we are getting the 0, that is the particle will be bound. If it is allowed, the particle is allowed on this potential well, then it will be bounced back along the B. So this is now all about the wave function, that is uncertainty principle, and according to, from that uncertainty principle we get the Schrodinger's dependent, and this according to that, according to this, up to this point it can be bounced back. Okay, thank you.